welcome, good evening. Welcome to this episode number 8 of Learning Amiga Assembly with Docster. Docster is not me, okay? I am I'm normally known as either Prince Phase 101 or Phase 101. I prefer Phase 101. Hello, Docster. As I was saying, Docster is not me, but the person that just wrote in the chat. I was doing this series and he started doing the examples or sending me examples, so I included his examples and I named this series after him for all the help that he gave related to this series. So yeah, thanks to Docster basically. Let's start with the usual thing. Let me go to the browser. So guys, as always, all I ask is that you go to my YouTube channel and like and subscribe on my channel and like the video so that YouTube shares more my videos basically. Under each video there is this button more, which if you click on it you will see more information, and most of the time you get sources also related to that video. Besides YouTube, I have my Phase 101 page on Facebook, which I would like to change eventually. So besides my Facebook page, I have my Facebook group and my Commodore Dev Facebook group. Please like, join, follow any one of these, and it's my Phase 101 page is for everything that I basically announce. Today I didn't even announce this stream, as normally I do. The Phase 101 is Facebook group is related to anything to Phase 101, and the Commodore Dev is related to anything Commodore. I also have my Discord group or server. Please join there if you want to get in touch with me. I can assure you that I reply quickly there. If you send me a message on Facebook, I do reply, but I take my time, so be warned there. Besides that, I also have a Telegram group if you do not wish to neither use Facebook or Discord. You can send messages there. If you want to go that extra mile, you can support us on Patreon or on Ko-fi. They are identical. You get, in this case it's still 101 posts to unlock, but actually there are 4 more, so it will be 105 soon, which, because I have uploaded them, I just haven't made them available for you to watch videos related to dev on Amiga. This is besides what you have on YouTube. Besides that, I remind you that I have this page related to Amiga Dev with links related to Amiga development, which I update. No, I don't want to say constant. I'm constantly updating it, but it's not every week or so. And I only do things which I only add things which I think are good for beginners. So this page is mainly with information to get you started. Then of course you need to continue looking around. For this series we are using also the Easy68K assembler or editor, besides ASIM Pro or ASIM 1, because it's the same thing. ASIM Pro is ASIM 1, but with some coloring basically. There's no difference. If you're on Linux, you need to use the 68000 simulator. But I do recommend the EC68K if you are on Windows. It's quite a good one to test the instructions. It's really good. So yeah. So let's pass to the Amiga, and I click here. Let's read the file. Now I'm going to do revision of the div instruction for two reasons. One is that last Sunday, okay, I'll give the points. I was saying last Sunday, I let's say got confused between the 68020 and the 68000, the difference between them. So basically, that's why I am going to do a revision of the div instruction. Also, that confusion made me look into I went into, how to say, I went and looked deep into the instruction of how it really works. So hopefully today I will be able to deliver this in a more better way, let's say that. So the div view, as I said last week, is the instruction which does unsigned numbers. Okay, it works like this. The destination can be a long word which is divided by the source, which can only be a 16-bit a word, basically a 16-bit number. Okay, the value, okay, goes into the destination, not the value, the answer goes into the destination, with the low word having the whole number, and the remainders goes into the high word. Okay, so this is quite important, and this is why you are seeing that source is word, destination is long word, but actually it's destination up here over source. Okay, and the result goes into destination. Okay, you can see it's a long word result. The flags affected are the N, Z, and V. Okay, the carry is always cleared. Okay, and the extended bit, nothing happens to it. If you attempt to divide by 0, causes an exception. I mean, you get a guru, basically. That's what it means, getting an exception. So let's execute it, or trace it. So we're clearing the registers. Now we move finally on PC. What is finally on PC? So we move 1000 into the 0. We divide that 1000 by the value of 233, and notice what's going to happen in the 0. You get 7 in the low word, and 9b is the remainder. Now we're going to move 18000 into the 1, but notice the 1 is a word. Notice that the 1 is a word because it's the source. Okay, so from 18000 we're going to use the 8,000. Okay, so what we have in the 0 division by 8,000. Okay, which gives us, okay, 136 remainder 7. Okay, that's the answer to what we had in that's the answer to 9B0007 division by 8,000. And remember, everything is unsigned, so everything's plus as a value. So let's do the next one. Now on this one, this is signed, so we are using it's the same like unsigned in the sense we have a long word divided by a word. Okay, so destination is a long word, source is a word, and the result is in a long word, but the values can be signed. Okay, so the bit is in the most significant bit indicates the sign of the number. Now this is where I got confused last week, so I'm just going to say it out loud. If you try to divide a number, because you have a long word now, no, and you try to divide it, say, by 1, like what Honey told me last week, okay, you will get an overflow because the result cannot fit in a 16-bit word. Okay, so dividing by one, it doesn't give you a guru. Okay, it works. So I was saying, if you try to divide, you know, normally you don't do this, you know, you don't go and divide by 1. Okay, so let's be honest there. But you can divide, let's say, the same number by 2, and the result will still not fit in a word. Okay, if it doesn't fit in a word, you get an overflow and you get the V flag, and this is quite important, so you need to do checks on this. Okay, so the same thing happens for unsigned. So signed and unsigned both have the same issue, so you always need to check for the overflow flag. Besides, you know, you need to also check for the if the result is a minus or a positive number. So, and I'm going to read this time from what I'm going to read this time what I have written in the description. Divide the destination, and I'm going to read it so I'll be precise this time, okay? Divide the destination operand by the source operand, okay? And remember, the destination is long, the source is word, and store the result in the destination. The destination is a long word, and the source is a 16-bit value. The result, i.e. the destination register, is a 32-bit value, arranged so that the quotient in the lower order word and is a 32-bit value arranged so that the quotient is in the lower order word and the remainder is in the upper order word. Div performs division of 2's complement. Okay, remember last week I explained 2's complement, or the week before, I can't remember exactly. I will do a revision of signed numbers today if I managed again, because that lesson I have extended. I mean, we have covered more. So now I will extend a bit more of what we have learned about signed numbers. Div performs division of 2's complement values. An attempt to divide by 0 causes an exception, of course. For divs, the sign of the remainder is always the same as the sign of the dividend, unless the remainder is 0. So notice the conditional codes. What gets affected is the negative flag, the 0 flag, and the V flag. So depending on what the result is, those will be set. So again, if the result does not fit, I mean, you need to, think about it. If it doesn't fit, then obviously you have an overflow, so you need to check it. So either you stick to 16-bit numbers, so you don't get the overflow, or if you stick to 32 over 16, then you might have an issue. Okay, so let's execute the code, and I also added a lot of more examples than last week. Okay, so we're clearing the 0 and the 1. We're moving 1000 again. Okay, and we're dividing it by 2 to 3, and because the 2 to 3 is a positive number and the 1000 is a positive number, we get the same result as before. Okay, but now, okay, we have 1800. Okay, and that is going to go into D1. Now this will generate a different result than before, because the 8000, remember, the D1 is a word, it's never a long word. D0 is the long word, which is 9B0007. Because 1000 is minus, indicates minus, it's minus 22768, so the result will be dividing by minus 32768, whatever that that number that we have in the 0, which is a positive number, okay, into, because it's a long word and the value of the 9 has got a 0 in front of it, okay, so it's a positive number. The result will be different. No. There are different instructions. There are more instructions. Let's say that, because I will be confusing people. Yeah, there are more instructions because it has an FPU built in and different ways of doing things. So notice the result. The result is FECA. It's a negative number in the lowered, and the remainder is 7. Okay, so things change. Okay, from the previous, from div unsigned to div signed. Okay, now I'm going to do the and notice that we have the M flag set in this one, so to indicate we have a negative number. I'm going to do the same, not the same, I'm going to do what Dr. Hani said last week, some of the examples that he said, and to do the division by 1 in this case. So 7FFF division by 1. Okay, and notice it's fine, okay, because we have a word, division by 1, and the result, it's okay. Now the 7FF division by -1, and notice what happens. The answer is 8001, and remainder is FFF, and we have a negative flag, the negative flag. Now -2, sorry, And notice the -2 in the 1 is FFFFFE, okay? Just to... And remember, source is always a word, destination is a long. So the 0 is the 7FFFF, okay? So we're dividing the 7FFFF with the FFFE, which is a minus, which is -2. And you got the result, okay? So it's still fine. Now we are adding more, so but I'm adding more digits basically, and -3, and you can see it's the same thing. It's 3, okay? Again, and we get 1. So basically we had -1 with division by -1, so we get 1, no? 1/1, it's the same it's the same thing, you know? So and this continues basically. What I forgot to tell you, I'm just going to run them again. I forgot to tell you something. So these are signed. Now notice every time the flags, okay? Notice how when we do the MULS, how the flag is set. So when there is a negative number, you will have the N flag set, okay? Like we're moving -2 into the 1, so the negative flag was set. But then we are doing a negative number dividing by a negative number, so we get a positive value, basically. So that's why we have 2. Hello, Proton. And the same thing for -3. Okay, so this example was written by Docster, so I'm going to go through it again. Oops. So we're clearing the 0 and the 1. We're moving that value into the 0. Okay. We're moving 2 into the 1. It's divide signed. Now notice I have dot long there. Okay. Although I had dot long there, the source was a word. Okay. The only thing I want to comment, okay, and here is where or maybe I should not comment, let's say that, but I want to be clear. I'm running this on a 68030. The 68030 has got long, can support dot long. So I just wanted to make you aware that it can do that. But notice the value can still not be stored. So the value is a negative. So notice that the N flag was set. Okay. It could be there's an error. Proton, what was the error in the comment? Ah, yeah, it's not. Yeah, but okay, I'll correct it. But yes, thank you. Yeah, it's not -10 because I think I also modified this. That example was done by Docs, but I think I modified his source. So yeah, and I didn't update the comment. uh, okay, we're going to visit the test example. So basically, test instruction. Basically, the 68,000 has got a test instruction, and it tests for, it's like comparing with zero, basically. Uh, that's basically what it is, compare with zero. In fact, the operand, if you see the comments, the description, the operand is compared with zero. No result is saved, but the contents of the conditional code register, where the flags are set according to the result. The effect of test, effective address, is the same as compare immediate with zero, okay? Except that compare I instruction also, except that the compare I instruction also clears the V and C bits of the CCR. Okay, so there's the difference between test and compare I. It's the bits that of the bits that they set. So this instruction sets the M flag and the Z flag and clears the V flag and the carry flag. Okay. And we're going to see this. So I'm clearing the registers here. And by the way, I'm using clear to clear the registers each time because I noticed that the Asim Pro, for some reason, it remembers where the what the value of the registers were before you started it. So this is why I do it. Sometimes some examples will not work unless I do this. But if you start it for the first time, the registers are cleared. So yeah, just to make you aware. So we're moving that value into D1. And now we're testing .byte into D1. So notice that we are testing if the first byte is at 0, okay, in D1. And we should see the 0 flag set, as I said. Now we are testing word, okay, so D1 and the word that we have in D1, so D1100, D1100, okay, and of course the 0 flag is not set because we don't have 0 there, okay. And now we test long, so the 0 flag is not set, but the M flag is set because we have a negative value. Hello, Amiga. Welcome to the stream. So, we are moving a word FFOO into the label, okay? Now, this is instead of against a register, against memory, okay? And it's the same thing. So, test.byte in where label is, and we have 0, 0. No, so the 0 flag will not be set because the first byte is FF, right? Yeah, it's a negative number. So we were checking the FF, okay, not the OO, okay. Now we are checking at label but +1, so we are checking for the OO, and of course the 0 flag here will be set. And now we're testing word, okay, and of course the 0 flag will not be set, but the negative flag will be set because we have the most significant bit is set. So this is the test instruction, and as I said, it's similar to compare with immediate 0. Just know the difference of the flags. Now the next instruction, I do not consider the next instruction that I'm going to do as a beginner's instruction, okay? However, I'm going to cover it. So this instruction, I have to say, okay, I'm going to talk from my experience. Maybe here is Proton, he can say other. If you look this instruction on the forums related to Amiga, they tell you to avoid this instruction, okay? There is something that the chipset of the Amiga doesn't like about it, because it waits, it steals the bus and waits on the bus, this instruction, okay? However, when I used it, okay, and you're going to see it here, nothing happens, it works, okay? So I don't know if it's when you're doing something particular with the blitter when this happens. I've never used it to be honest, when I was doing something with the blitter personally, but as you see with my note at the bottom, use with caution on Amiga. This instruction logs the bus, okay? If custom chips DMA is being used, it can halt the Amiga. Better use bset and btest. So, as I said, I did not have any issues with it, but I found many people in the forum complaining about it or saying not to use it. So I believe that there is something about this instruction that can cause issues on the Amiga if other people are commenting on it, okay? What does it do? It tests and sets the byte operand addressed by the effective address field. The N and Z bits of the CCR are updated accordingly. The high order bit of the operand, which is bit 7, is set. So only bit 7 is affected here, okay? And you're going to see it in the
Mamma mia!
Mamma mia.
Here we go again.
You gave me a skip.
Read my message.
I was saying it's bit 7 that gets affected. This operation is indivisible and uses a read, modify, write cycle. Its principal application is in fact, this is the other thing that I found about it. Basically, if you have a multitasking application, okay, and you try to have a task, stop the task, use another task, this instruction is there in the 68000 to help you do that, okay? To say to the task, okay, you set the bit or the most significant bit of the task and say, okay, you are locked right now, and you execute this process, or you are unlocked, so something else can be executed. I'm not an OS person that writes OSs, okay? So I cannot really comment on it. I'm not I'm not an expert when it comes to writing operating systems. So, but this is what I read about it, and what many books say about it, why it is there. Okay, so let's see what. Let's see the example. Sorry, I was not reading all the comments. Let me go through the comments. We're going to move 12 into the 0, okay? And notice which bit is going to be set when we do test and set of the 0. And I wrote the binary value there. So notice we're going to get the most significant bit set. Okay, now I have created like a loop to show you how it is used in, let's say, in multitasking operating systems. But as I said, it's not really my thing. So I try to simulate it to the best of my knowledge. Let's say that. I never wrote an operating system, and it's not really something that I like doing. So we have a list of bytes at spin lock, okay? And we are going to compare each value till the test bit, okay, tells us it's a 0. Basically, and notice we have 1 right now, and the test bit, we wrote the next one, and the 0 flag is not set. So only when we have 0, basically, the bit will be set. And I'm just going through each one. So we read 80, we're going to read FF. And now 80 is going to read 0, and is going to go into the 0. Okay, so now we're going to test 80. Basically, I did the move.byte 80, 80 to show us which bytes we are reading, okay? So notice that when we move .byte 80, 0, we already have the Z flag set. So basically, bit 7 is not set. Actually, give me a second. So bit 7 is not set since the value is 0. And basically, we have a lock. As I said, I think this instruction, I covered this instruction so that I make you aware of the caution that you need to take to be careful when you use it on the Amiga, because of the custom chips, more than anything else, to make you aware of the issue. It's not something that I would use. I would avoid using it and use the bit set and bit test. But yeah, it's good to know. Let's say that. So so what you need label. At label there is going to be ff00, but test b.label is going to test ff, not d00. So what is about the big Indian of the Amiga that you want to talk about, Proton? Okay, would be more efficient example to show test B memory to have a long um Proton, I have already covered this. They know, okay? Proton, no offense, but you came, this is episode 8, okay? So you expect me to be in episode 8 and not have not covered Big Indian, okay? So they know that the address, how addresses are stored on the 68,000. But yeah, it's stored as if I had to do let's do this then. M and label, okay? You see FF and the 00. That's how it is stored. So at label, the first byte is FF. Label plus 1 is the 00. I have already covered this, Proton, just to make you aware. I think it was lesson 2 or lesson 3 of this series, and we are in lesson 8. So let me, just to put what Proton said, let's do a revision of it. I don't mind doing it, to be honest. 2211, okay? And let's, oops, and let's execute it. Oh, not move word now. Move dot where dot long. So I'm going to stop here, okay? Just to show you how it is stored. M label. So there is the 33221100. This is the opposite of the 6502, okay? So the first byte, let's say that, or the first word is the high word, okay? The second word is the low word. Just to make you aware of, so if I had to run this example now with the value that Proton gave, okay? Now notice what's going to happen. When we are testing, so the first one, the 0 flag will not be set because the value is not 0, it's 33, right? Now, label plus 1, the value is 22. So the 0 flag will not be set, okay? And test.word, okay? The value, the 0 flag will not be set, and not even the negative flag will be set, because the value, we have 3322, okay? As you can see there. So it's a different, you need to, when it's in memory, you need to keep in mind how numbers are stored in memory, basically. And I think that is what Proton was trying to say. Does that answer it, Proton? Still there, Proton? Does that answer it? Yes, exactly. Highest bytes are stored first, not last. Okay, we're going to talk about the negate instruction, the neg instruction. Okay, so the neg instruction does a 0 minus destination. Okay, it's always 0 minus destination. In the background, this is what happens. Okay, and the result is in destination. This can work on byte, word, or long word. What it does is subtract the destination operand from 0 and stores the result in the destination. Now, here is where 2's complement is at ease on the 68,000. Okay, the difference between the not and the neg instruction is that the not performs bit by bit logical complementation, while the neg performs a 2's complement arithmetic subtraction. Okay, all bits of the condition code registers are modified by the neg operation. Okay, so the conditional codes X, N, Z, V, or C can be affected. So if you recall, I don't think if it was the last episode, but the one before it. Okay, so episode number 6, I showed 2's complement numbers, how they work, what they are, and I even gave examples of how to convert from +4 to -4 and vice versa. But I used the instruction, or I simplified the instruction, and based also what Docster have done, although I edit a lot more, basically by using the method that is done on the 6502, let's say that. But on the 68,000, 2's complement, it's easy to convert from, if you have -4, if you have +4 and you want to the negative number of it, which is -4, the neg instruction will do it for you, basically. Hence, we're going to see that here. So you can see I have cleared the 0, but so negating the first byte, we get of the 0, 0 minus 0, it becomes 0, no? So it's still 0. But if we have 1 in the 0, okay, negate byte of the 0, we get the FF, okay? So which is -1. So it did 2's complement of it. Okay, same thing for 2. Okay, it's going to be FE. And notice the flags, how they're being set. Now, notice the difference between the... I'm covering a bit the not instruction, even though I haven't really covered it yet. But notice the difference between the not instruction. Okay, so if we clear the 0 and we do not byte the 0, it becomes FF. So it's not 2's complement, okay? And if we move 1, it becomes FE, not FF. So it becomes -2. In reality, if you do not, okay? And same thing if we have 2 and we do not not of what we have in the 0, which becomes FD. And here I have more examples of the negate instruction of this value, long value into the 0, and I negate each byte, word, and long word basically of it. So we're going to negate the 77, and becomes 89. Now we're going to negate the FF89, okay, which becomes the 0077. And now we're going to negate the long of what we have in the 0, which is 12340077, and becomes that number. Okay, so is it clear that the negate instruction, okay, gives you 2's complement just by one instruction without going to do an not and then add and then end, sorry, as we did, or add as we did in the, as you do in the 6502, okay? And in fact, yeah, I will come to a later stage about it. So I will come to 2's complements in a minute again. Let's do the clear. So I've been using clear, but I've never explained it. Clear works on data registers. It doesn't work on address registers. So this destination is cleared. By the way, the size can be byte word or long word, and it obviously it sets the register, or it says it clears the register, makes it 0 basically. This destination is cleared with all zeros, basically it's loaded with all zeros. The clear instructions can be used to clear an address register, okay? To clear an address register, I said what needs to be done. Use up the address with the same address, or you move .long. I mean, the sub is quicker. Important, note that the effect of clear in implementation, or of CLR implementation, is that this is important on the Amiga, okay? Note that the side effect of clear implementation is a read from the specified effective address before the clear operation is executed. Why I'm mentioning this? The custom chips, the registers of the custom chips, if you need to think what you are doing on the register, okay? Some registers in the custom chips, first, if you do a read, you can affect certain things like clearing things. So here, okay, you are doing a read, okay, from an address, because it works on memory also, okay, and then it sets the bits, then it sets the contents to 0. So the fact that it's reading, so this is why under certain circumstances, there I have a missing word, Amiga hardware registers, I should say, okay? This might cause a problem, okay? So it's not always the right instruction to clear a register on the Amiga, to Amiga hardware registers I'm talking about now. So note, keep this in mind, that it does a read and then it clears and then it does a write, okay? So basically you're reading and then writing. What it does, it sets 0, the negative flag, the 0 flag is set, the V and C are 0, basically cleared. Let's so we're going to move this value into the 0. We're going to clear byte, okay? So we're going to clear the 76 from the 0, Okay, so it's 0. We're going to clear word, so the 9800 is going to be cleared, and then clear long. We're clearing it basically. We're going to move another value into 80, and we are clearing, okay, the 80. Basically, we're setting it to 0. So I need to do. Okay, so the next one I'm going to do. Oh, there you go. Uh, so this is what we did. I think episode number 6 about assigned numbers. Okay, and we went through all this explanation, and we did these examples, okay, where we had 4 and it was in a byte, and we converted it into -4 by using the not and add. This is the 6502 style, as I called it here. Now I updated the notes, okay? And this is also what Docster had done back then. And I kept it like that because I know I would have come back to it using the negate instruction. So, and we did it for byte, for word, okay, and for long word, okay, every time we get the number back. But now, notice, we're going to do the same thing using the negate, okay? So now, it's the 68 way, the 68K way of actually doing 2's complement, okay? So we have 4 into the 0, we negate it, we get the -4, okay? We get it back by doing the negate b again, and we get the 4. And we were working on a byte. And we continue like this, working on word now, okay? I mean, I always kept it, I always kept it 4, just for the sake of it, I just needed a value, yeah. So this is we are doing this on a word now, and now we're going to do it on a long word, and you can see we got -4, and now we get 4 again on a long word. Yes, Proton, do not get offended. I didn't mean to offend you, but what you are, I'll show you so you understand, okay? Because maybe because you see, we are in episode 8, okay? If I go to episode 5, there is the move instruction, okay? If I go back, episode 6, there is the move quick instruction. So I cover the details of this, each one by one. And this is what I'm doing. So going back to move quick is not going to help me. Or it's not going to help the others because we have already done it. Okay? I do not want to confuse people. Okay? I'm just explaining that instruction. So I understand your point and you're trying to help, but this is what maybe you have not seen or haven't followed. That's why I am saying this. Not because you don't know it. I know you know it. Okay. So we're going to do the compare instruction. Okay, now the compare instruction, and I'm going to, I forgot to start the sheet. Give me a second, guys. Uh, let's see if I manage to find it. Okay, I think I managed. And let's switch to the Excel sheet. No, Proton, don't, no worries. I just want to be careful not to confuse people. So that's all. I mean, I don't mind if you comment, but if I tell you if I've done it, I have done it. You know, I haven't skipped it. So I do not mind being reminded because I can skip things myself. So I don't mind at all. So I see that my screen has vanished. My camera has vanished for some reason. I think it's this. Yeah, I had it off. So the ones in green we have covered, right? What I want to remind you is that the compare instruction, okay, we write compare, okay, but behind the scenes, the assembler, okay, will convert these for us, okay. So we always write compare, but actually if we're using an address register as destination, then it will do compare A. If we're using an immediate number, then it will do a compare I. Okay, if we're comparing memory, okay, against memory, then it will do a compare M. Okay, just to remind you that we are doing, when we write compare, it depends on what type of instruction we are using. It will do one of these. Okay, and you can find this, as I showed you in previous episodes, by disassembling, and you will see that a compare will be a compare A. Okay, so the assembler, I was calling it AI. I think last one, it's like the assembler has some kind of AI and knows that we want to say compare A. Okay. Yes, move quick is faster. Move quick has got one caveat, let's say that, because it's sign extended. So you need to be careful of this. Yeah, of course. This is if you are doing a cleared a value of 0, no? That's what I meant, or at least that's what I understood. That's what he meant, no? Docster, is that what you meant? Yeah. So what I wanted to show you also, that here the ones in green, is what we covered so far, and I have highlighted the test and set instruction, okay, to show you that although it's not for beginners, I want you to be cautious about it. Hello, Night Shift. So, the ones in yellow is what I'm trying to cover, but I am going to avoid to cover these today. And because, yeah, I shouldn't cover them today. I might confuse. Let's say it's a topic that I want to do on their own. These instructions. So, just remember what the assembler does behind the scene, okay? For us. So let's go to the Amiga. Yes, we did. Yes. I think it was episode 5. I think it was 5 when I did sub and ed. No. So Proton, actually, you reminded me of something. Proton, good one. I'm going to go back to the screen here. What I am covering, okay? I have, let's say, labeled the instructions, okay? Those that are for beginners, because this is for beginners, and those that you do in advanced or they are for a higher processor, okay? And those that has got B, I am going to cover, okay? Those that don't, okay? You will learn them as like anyone else. You'll come to the you'll use them once you know more about these instructions, basically. The edX, the extended bit, I'm not covering any instruction which uses the extended bit. So like negx, for example, here, I'm not covering it. Okay. I felt that I should not go into the details of the. First of all, I covered them. The extended bit, I covered it quite deeply when I was doing the book. But this is for somebody to start when they are, when you are first trying to do 68,000. So going into such instructions is not. It's not something that you will start using from the beginning. I'm just covering the instructions that I think, well, my judgment, okay, I could be wrong, that I think one should know to start doing something on the Amiga. Let's say that. And as I said, I covered the tasks instruction because I think it could be misleading in thinking that you can use it, but then you will have issues when you use the custom chips. Anyway, good point though. Let's go back to the Amiga. Which error you saw? Proton. I mean, yeah. Which do you remember which example was it? That's what I am. The first example we did. Let me go back. The first example we did. It was either when I was doing the div instruction or when I was doing the test instruction. I can't remember where you joined. Divs. Okay. Yeah. That is. Yeah. So what about divs? Let's see. So the div instruction, okay, is always, as I said, so that is not an instruction of the 68000 Proton. That is a 68020, as far as I know. So in 68000, okay, and I have a book here also, just in case I make mistakes and I need to reference or somebody challenges me, because I'm not perfect. The div instruction, the 68000 instruction, okay, is always a long word divided by, which is 32, divided by a word, okay? There's no other format, basically. Yes. And that's the only one that there is. Yes, exactly. Divide 32-bit value by 16-bit value. Exactly that. Let me get back to it. This was the vest, no? So it's always long word divided by word, result in long word. Yes. Good. That's why I said, that's why I said I'm running this on a 68030, not on a 68000. So it understood it. That's why I said that. Yes. But I do not want to go into that. I do not want to go into. Yes, I know. Proton, I know. It was in this example, actually. It was the Docster one. Okay, I should have not have .l there. It should be like that. Okay, that's the right way of doing it on 68000. Because .long is as you said. No. It's I understood. It's it's uh, it's you saw right. There was L, but it shouldn't be there. Yeah. You saw right, Proton. You saw right. Look at Docster, what he's saying. Yeah. Actually, I'm going to update it because that should really not be there. Okay, let's go back to the compare. Resistance is futile. Anyway. So. Oh, I'm still in the. Okay, I am in the compare instruction. I make this mistake up to you. One moment. Should I wait for something, Proton? Anyway. So. Stay tuned. Okay, so put in your comments, and I will. I'm going to explain the compare, and then I'll go back to what you said, just in case. Let's check the compare. Okay, so we're moving 1010 in the 0. Okay, and look, I have also a mistake there because I wrote 1000 in the comment. Anyway, and we're moving 10 into the 1. So move dot long and that number into the 2. And now we're going just to compare, and we are going to check the flags. Now, before I run that, because I haven't really explained the compare properly, okay? Let's do that. Okay? Compare, okay? The operation compare does destination minus source, and what it does when it does this destination minus source, it sets the conditional code registers. I mean the flags, basically. It can set the N, the Z, the V, and the C. Okay? So the negative flag, the 0 flag, the overflow flag, and the carry flag. It works on byte, word, and long word. As you can see in the description, subtract the source operand from the destination operand and set the conditional codes accordingly. The destination must be a data register. Yes, it works on the compare works on data registers. This destination is not, so it doesn't work on address registers. That's what you need to keep in mind. The destination is not modified by this instruction, so nothing happens to the destination. We just do subtract, basically a subtraction from destination minus source, and we set the flags. And now you are going to see, okay, what happens to the flags when we have, of course, there is more to it, okay? I'm just saying, I'm just explaining the compare instruction. Of course, we haven't arrived to the branch instructions, okay? So I will be covering that in a later episode. So now just know what the compare does and notice the flags. That's the main aim of this. So we're going to compare, and it's a byte, D1 with the 0. So we're going to subtract what's in the 0, okay, the byte, which is 10, minus 10. So basically, we're going to get the 0, and so the 0 flag will be set. Okay, and as you can see, the 0 flag is set. Oh, Docster, nice to hear. Now we're going to do a compare.long, and we're going to compare D0, D2 with D0. So we have D0, the 1010, minus what's in D2. Of course, the 0, okay, is a smaller number than what's in D2, okay? And because that, we have 10 minus 1, 2, 3, 4, 5, 6, 7, 8. So we have a negative number there. Okay, so the N flag will be set, but the 0 flag will not be set. Okay, because the value is not 0. And as you can see, the N flag was set, there was a carry, and the 0 flag was not set. So those were the changes when we execute these instructions, when we do this instruction, or when we compare values. Right now, we were talking about data registers, okay? This is why it's it's compare, it's CMP, okay? And this is where you need to keep in mind what the assembler is going to do behind the scene, because I told you it works with data registers, but now we have compare A, okay? And compare A, okay, works with address registers. Okay, we think that compare can work with address registers and with data registers. Yes, Proton. I think if it doesn't, send it to my Discord. Post it. If it doesn't, I will look at it from Discord. So behind the scenes, when we write compare, it will change the instruction. It will change the instruction from compare to compare A. Okay, that's where the AI, because everything is AI these days, the AI of the assembler, what the AI of the assembler does for us behind the scene. So I'll finish this Proton and I will have a look at it. Okay. So it's the same thing. It subtracts the source operand from the destination, okay, and set the conditional codes accordingly. The I'm reading. Sorry, guys. I'm going to read it again. Okay, subtract the source operand from the destination address register and set the conditional codes accordingly. The address register is not modified. The size of the operation may be specified as word or long word. Yes, because we're using address registers, we can only specify word or long words, okay? Also, notice at my note, okay? Word length operands are sign extended. The 68,000 have a habit of extending the sign with certain instructions when you're using word. So you always need to keep this in mind. Okay, so it will sign extend it to 32-bit. Okay, before the comparison is carried out. So we're going to clear the registers because, as you can see, when I started the debugger, they all had a value of the previous example. So we're going to clear, and I'm using this method so that you can see that you can clear an address register like this also. So I'm clearing A0 and A1. Okay, so we're moving that value into D1, we're moving that value into D2, and we're moving that value into A0, okay, and we're moving that word into A1. Okay, now notice I wrote the instruction compare A, but if I did not write it, Proton, send it to Discord. It's not going to let you, I think. If I did not write compare A, the assembler AI will do that for us. Okay. So we're going to do a compare D1 with A0. So A0 has got, and it's a compare.long, okay? It has got that value in it, and D1 has got the same value in it. So what's in A0 minus what's in D1 will get a 0, so the 0 flag will be set. And you see this is the 0 flag set. Now we're going to do a compare word, and remember, compare word is sign extended when it comes to an address register. So A1 has got the value of 1000, okay, and we are subtracting 1000 from D2, which is the big value that we have there, the 5678, because it's a word, remember. Now 5678 is not a signed number. Sorry, it's not sign extended because it's not higher than 7FFF. So the flags is the M flag set, and the carry flag, of course we have a carry there, is set, and of course the 0 flag is not set because the value is not 0. Now compare A, okay, but long this time. So 1000 with A1. Now A1 has got the value of 1000, okay, so then we will have 1000 minus 1000 is the 0 flag set again. Okay, so this one is against an immediate value basically. And you can see that the 0 flag was set. Okay. Okay, let's see what Proton sent me. Yes, okay, I'm going to show it, but this is not a beginner's. What I'm going to show is not for beginners, okay? But it's a way of doing it. Let me. I need to make it bigger first of all. And I'm going to switch the screen. Okay. So Proton sent me this code, okay? This is a multiplication, okay, of 32-bit number by 32-bit number, which the result will be, as you can see, 32 times 32 bit numbers. They produce a 64-bit number, okay? And he is using the MULU, so the multiply, and also the extended bit, okay? You can see this is where the extended bit comes in, but I'm not covering that, okay? It's not something that I consider you need to know right now. However, notice his usage of add the instruction with the extended bit, and same here, okay? Yeah, that's actually good. Yeah. Thank you, Proton. Here is the URL for those that want to copy the source and have a multiplication using 32-bit by 32-bit. As I said, this is advanced, okay? So not a beginner's part, but since Proton was nice to share it, I'm happy to share it and make you aware that you can have bigger numbers if you want. Okay, so let's go back to the Amiga. Yes, yeah, good point, Proton. Yes. Yeah, it works on 68020 and 030 and above. So that's another thing. Yeah, I should have mentioned that. So again, we have compare I. Oh, I forgot to. One second, guys, because I need to look at my notes at the same time. Okay, so the compare I, it takes an immediate value. Okay, so destination minus immediate value. Okay, that's what it does, the compare I. We write just compare, as I said, but the assembler does compare I. Writes compare I for us. It works with bytes, a word and long word. And again, it subtracts the immediate data from the destination operand and sets the condition codes accordingly to the destination. There I have mistakes there. Subtract the immediate data from the destination operand and set the condition codes accordingly. The destination is not, there should have been a full stop there. The destination is not modified. Compare I permits the comparison of literal, of course, literal with memory. It can also compare against memory, of course, not just with the data register. Flags affected, like the previous ones, is the negative flag, the zero flag, the overflow flag, and the carry flag. Sorry, I'm correcting a bit my notes. Let's run the example. We are clearing the zero. And remember, since Proto mentioned it also earlier, this is move quick, and move quick is always long. Okay? Move long, and the value that we have in the zero. So we initialize the zero with that value. Then we're going to do compare, and we're going to compare a byte. So the byte in the zero, the 78 with 78 basically. So 78 minus 78, and the zero flag will be set. Now we're doing to compare the 5679, so one value higher. So the 0 minus 5679, so 5678 minus 5679. Okay, and that sets the negative flag. So because we have a negative value, the carry flag will be set, and the zero flag will not be set. As you can see, that's the result. And now we're going to compare that long value with the zero. So basically the zero minus that value, and the zero has got the same value as what we are trying to compare with, and so the zero flag will be set, as you can see there. If you have questions, please let me know. Actually, I skipped the question from Docster. Who uses compare A? Is it to make the source more clearer? No, I mean it's understood. Why I wrote compare A is for you to understand that it's a different instruction than compare, and you do not need to write compare A. You can write compare, okay? It's just to make the source clearer in this case. I don't know if, actually, if you find old sources, I don't think the assembler used to do that, but I'm not sure. I'm trying to remember the Sika assembler, the first one, the first ever assembler for the Amiga, let's say that. I don't think it did that, but I'm not sure. The first version I'm talking, because then from Sika there was Master Sika, and then Asim1 was born, basically. So I remember Sika, Master Sika, and then Asim1, and then also DefPack. Yeah, comment. I mean, yeah, no problem. It's not. I don't take it as criticize. What I want to make sure, because this is a beginner's course. Okay, let's say that. I just do not want others to get confused. That's all. So I'm very careful of what I say. Sometimes I limit myself what I say. So and now we're going to do the compare M against memory, basically. So compare M, I have a mistake there. That should be compare M, not compare A. Okay, guys, so that's a typo from me. So it is the same as the other instructions, so destination minus source, and it says the conditional code registers. It works on byte, word, and long word. So description, as you can see, subtract the source operand from the destination operand and sets the conditional codes accordingly. The destination is not modified by this instruction. Okay, so it doesn't modify the destination. The only permitted addressing mode is address register. Yes, this is an address register indirect. So where you have this, what I mean by my note is that this type of addressing mode where you have the address register in the brackets and the plus. Yes, I believe I said it. I'm not sure, but yes, Proton, you are correct. I believe I said this, that the compare instruction is a subtract. In fact, I'm writing it in my notes that it's a subtraction from destination minus source. So if you notice the operation at the top, I'm always saying destination minus source. So it's a subtraction, and then description subtract the source operand from the destination. So it's always a subtraction, basically. But yes, good point. I don't mind repeating things, especially if it helps beginners. So I was saying about the post increment. Okay, so it only works with this addressing mode when it comes to when you're comparing memory. However, this is what you need. So don't think you are limited, okay? The flags, okay? Affected are the negative flag, the zero flag, the V flag, and the carry. I mean, like all the rest, like all the other compare instructions. So I'm loading 80 and day 1 with the addresses of those labels, okay? And you can see the 80 and day 1 with the 26 ending with 2684 and 2688, okay? Those are the addresses that we will be working on. And we are going to move a word into 80, so the first label, label 1, and we're going to move a word into A1. It's for, guys, I could have wrote it in a lot better way. It's for clarity that I used it like I'm using it like this, where I have the define constant dot long, I put a label, and I'm using this as an example the way it is. So it's for you guys to understand better what's happening, okay? And now we are just going to compare, okay, what's in 80, okay? So and it's a byte, okay? So we're going to compare the 1 2 3 4, okay, with the 1 2 3 4. Now I could have said define constant word there. I used long because when I was writing the example, I said, okay, I didn't know what I'm going to write, but then I decided to use words instead of in for the address registers, for the values in the address registers. So because of that, the 0 flag will be set, and of course we act on that. Okay, if I do m label 1, you will see we have the 1 2 3 4. Yeah, and then the zeros, because I reserved, I said define constant long there, and then again 1 2 3 4 and the zeros. Okay, so I'm comparing the first word with the first the first byte, because it's compare byte. So the 12 with the 12. Okay, that's what I actually did. I'm not sure I'm understanding your last sentence. I mean that thinking of compare something, yes, and then thinking in C, set or not. Oh, I and then thinking is and then so you're talking about the flag now, and then thinking is C set or not is easier to think slash calc sub something. Yeah, okay. Okay. So what Proton is saying, instead of good point, instead of saying compare, okay, you can say sub, okay, because in your mind, okay, it's easier to think, okay, the destination is subtracting the source, okay, and you know the result like that if you do a sub, okay. This is a way of thinking, though, not what you write, okay? You have to write compare. However, and this is maybe my fault, because I'm used to that compare as a subtraction, okay? So I do not say sub destination minus source, okay? I just know that this is what's happening in the background. But yes, as a beginner, you can think like that. So I am, let me see something now. Yeah, so for this lesson, I actually thought I will be able to do the AND or XOR not, and then I'm going to do move revised, okay? The move instruction, I'm going to go into more depth about it now. I mean, I know I covered it all, but there is more to say. And because we covered certain instructions now, I can talk more about it. So, however, these will be in the next lesson, so I will copy them in episode number 9 now, and I will stop here today. So guys, thank you very much. Thank you very much, guys. I hope you have a lovely week. Next week. Thank you. Bye bye.